The story of how Bohr's revolutionary atomic model transformed modern physics begins long before Niels Bohr himself appeared on the scientific stage. It begins in a world where the atom was little more than an abstract idea, a theoretical grain of matter that philosophers speculated about for centuries without any proof of its internal structure. By the late 19th century, science had entered a new era of precision and experimentation, yet even the most advanced physicists struggled to understand what atoms looked like, how they behaved, and why they were stable. The classical world had provided powerful mathematical tools, and the laws of motion devised by Newton seemed capable of explaining everything from falling apples to the movement of plants. But when it came to the atom, the very foundation of matter, classical physics failed, and that failure created one of the biggest scientific puzzles of all time. Before Bohr, the most accepted picture of the atom came from J.J. Thomson, who imagined it as a solid sphere of positive charge, with electrons embedded like raisins in a pudding. This model gained popularity because it aligned with known electrical behavior and seemed simple enough to visualize. But then came Ernest Rutherford's gold foil experiment, which shattered the pudding-like view forever. By firing alpha particles at thin sheets of gold, Rutherford discovered that most particles passed through easily, while a few bounced back sharply. This meant that atoms were mostly empty space with their mass concentrated in a tiny nucleus. It was a revolutionary insight that completely changed how scientists viewed the atom. Yet it created an even larger dilemma. If the atom has a dense positive nucleus and negative electrons orbiting it, why does it not collapse? According to the rules of classical electromagnetism, a charged particle moving in a circular or elliptical path should radiate energy continuously, losing speed until it spirals inward. In this picture, atoms could not possibly remain stable, and all matter should instantly disintegrate. Something was terribly wrong with the classical understanding of nature. This was the scientific landscape. Niels Bohr stepped into a landscape full of contradictions, unanswered questions, and conflicting theories. Bohr was not only a brilliant physicist, but also a thinker willing to question the most fundamental assumptions of classical physics. He understood that if the atom was ever to be properly described, the old rules had to be modified or replaced entirely. At the same time, the ideas of Max Planck were beginning to influence the world of physics. Planck proposed that energy was not continuous, but came in discrete packets called quanta. It was a bold suggestion intended only to solve a specific problem in blackbody radiation, yet its implications were enormous. Bohr saw an opportunity in Planck's idea, a way to rescue the atom from collapse. The challenge before Bohr was immense. He had to reconcile Rutherford's nuclear model with the stability of atoms, while also explaining the mysterious spectral lines of hydrogen that scientists had been observing for decades. These spectral lines were like fingerprints of atoms, unique patterns of light emitted when atoms were energized. But no classical theory could explain why hydrogen produced such precise and discrete wavelengths. For many years, these lines remained a puzzle with no solution in sight. Bohr recognized that the key to understanding these patterns lay not in the classical world but in the quantum world that Planck had hinted at. Quantum physics was still in its infancy, a rough and incomplete idea, but Bohr had the vision to apply it to the atom in a way no one else had imagined before. Bohr proposed that electrons do not orbit the nucleus with just any energy, but with fixed, quantized energies. In other words, an electron could occupy only certain stable orbits where it did not radiate energy at all. This went against everything classical physics taught. There was no reason, according to Newtonian laws, for an electron to stop radiating energy simply because it occupied a specific orbit. Yet Bohr trusted the mathematical consistency of his idea more than he trusted classical intuition. He reasoned that if electrons existed only in specific allowed states, then they could jump between these states by absorbing or emitting energy equal to the difference between them. And remarkably, this difference corresponded exactly to the frequencies of the spectral lines emitted by hydrogen. The mysterious patterns of light that had baffled scientists suddenly made perfect sense. It was as if Bohr had found the hidden code that governed atomic behavior, a code written in the language of quantum principles. The impact of Bohr's model on modern physics cannot be overstated. It not only provided the first successful explanation of atomic stability, but it also bridged the gap between classical and quantum physics at a time when no one was sure how to reconcile the two. Bohr's model showed that while the world might appear smooth and continuous on a large scale, at the atomic level it behaves in discrete jumps and fixed energy levels. This idea was so radical, so counterintuitive, that many scientists were hesitant to accept it at first. But the empirical success of the model spoke for itself. It explained observations that classical physics could not explain, and it did so with a mathematical precision that was impossible to ignore. Hydrogen, the simplest of all atoms, became the testing ground for Bohr's model, and it passed every test with astonishing accuracy. Yet Bohr's idea did far more than explain one element. It opened the door to a new understanding of nature itself. It inspired a generation of physicists, including Werner Heisenberg, Erwin Schrödinger, and Wolfgang Pauli, to explore the quantum world more deeply. Their work would eventually develop into full quantum mechanics, a framework that describes the behavior of particles with unprecedented accuracy. Without Bohr's bold conceptual leap, quantum mechanics might have developed much later, or in a very different form. Bohr had not only solved a problem, he had created a new intellectual landscape. And in that landscape, old assumptions crumbled while new principles took root. The idea that energy is quantized, that electrons occupy fixed states, and that atomic behavior follows patterns that defy classical intuition, all of these insights stemmed from Bohr's pioneering model. What truly made Bohr's atomic model transformative was not just the science itself, but the way it changed how physicists approached the unknown. Bohr introduced a mindset: when classical ideas fail, one must be willing to step beyond them. He showed that the universe might operate according to rules that seem strange, illogical, or even impossible from the perspective of everyday experience. Yet these rules are real, and they govern the smallest scales of matter with extraordinary precision. Bohr taught the scientific community that accepting the quantum nature of reality was not a surrender to mystery, but a pathway to deeper understanding. His model demonstrated that atoms are not tiny solar systems but quantum structure, governed by principles unlike anything in the macroscopic world. This shift in thinking was monumental. It moved physics away from classical determinism and toward a probabilistic, quantized reality. Bohr's model also laid the groundwork for the technologies that shaped the modern world. Every laser beam, every semiconductor chip, every device that relies on quantum principle can trace its origins back to the insight Bohr introduced about quantized energy levels. He may not have predicted these technologies, but he provided the theoretical foundation that made them possible. That is why Bohr's model is not just a historical milestone, it is a living framework that continues to influence science, engineering, and technology even today. The transformation that Bohr brought to physics was deep, far-reaching, and irreversible. His model became the turning point where science shifted from the familiar laws of classical mechanics to the strange and beautiful world of quantum mechanics. It was a transformation not just in knowledge but in worldview. For centuries, scientists believed that if they understood the motions of objects, they could explain the universe with certainty. Bohr shattered that certainty and replaced it with a new kind of understanding, one that embraced discontinuity, quantization, and the idea that nature at its deepest level behaves in ways that challenge our most basic assumptions. Bohr's revolutionary atomic model continued to reshape physics long after its first introduction, influencing not just how atoms were described, but how scientists thought about reality itself. The model was more than a scientific proposal, it was a philosophical challenge to centuries of classical thought. In the classical world, continuity was the norm, motion was smooth, energy changed gradually, and nature followed predictable paths governed by deterministic laws. But Bohr's model declared that, at the atomic level, continuity breaks down. Instead of infinite possibilities, nature chooses from a discrete set of allowed states. Instead of gradual changes, electrons shift abruptly, jumping from one orbit to another without ever occupying the space in between. This concept was so startling that even Albert Einstein struggled to accept its implication, famously questioning the suddenness and apparent randomness of quantum jumps. Yet Bohr was unwavering. He believed that the quantum world required new rules and new ways of interpreting experience, even if the classical mind resisted. As more experiments confirmed the predictions of Bohr's model, the scientific world began to realize that quantum behavior was real, not metaphorical. Hydrogen's spectral lines had long been a mystery, lines that appeared at precise, seemingly arbitrary wavelengths. Classical theories failed to explain them, but Bohr's model fit the data with mathematical perfection. When electrons fell from a higher energy level to a lower one, they emitted light, a specific wavelength determined by the difference between the two energy states. This simple rule, grounded in Planck's quantum hypothesis, matched the spectral lines so accurately that Bohr's formula for hydrogen became one of the most famous successes in the history of physics. The precision of these predictions was not just a technical triumph. It validated the deeper idea that atoms were governed by quantized laws. The fact that nature followed these precise quantum rules, hidden beneath the visible world, suggested that the universe was far more structured and intricate than classical physics had ever imagined. The significance of Bohr's contribution became even clearer as physicists explored atoms beyond hydrogen. Although the original Bohr model could not perfectly describe more complex atoms, the basic insight remained intact. Electrons occupy quantized states, and energy changes occur in discrete steps. Later refinements by Schrödinger, Dirac, and others expanded this idea into a full quantum theory that could explain the behavior of all elements, chemical bonding, electron clouds, and countless other phenomena. But even when these later models replaced the details of the original Bohr picture, they preserved its essence. The quantum nature of energy levels, first proposed by Bohr, survived and became one of the cornerstones of modern science. It was as if Bohr had drawn the outline of a map that future explorers would fill with stunning detail. Without that outline, they might never have known where to begin. As quantum mechanics matured, the philosophical implications of Bohr's idea grew even more profound. Classical physics had offered certainty. If one knew the position and velocity of a particle, one could predict its future indefinitely. Quantum mechanics, born partly from Bohr's atomic model, shattered this ideal. Instead of precise predictions, the theory offered probabilities. Instead of particles with definite paths, it offered wave functions that spread across space. Bohr embraced this shift, arguing that at the atomic level, classical concepts lose their meaning. An electron is not a tiny ball orbiting the nucleus, it is a quantized entity whose behavior cannot be described without acknowledging the limits of measurement and observation. Bohr's complementarity principle, which he later articulated, emphasized that particles can behave like waves, and waves can behave like particles depending on how they are observed. This idea became one of the philosophical foundations of quantum mechanics, shaping the way scientists interpret the nature of reality. Bohr's insistence on redefining classical ideas was not an easy process for the scientific community. Many physicists resisted the idea that nature could be discontinuous or probabilistic. Einstein famously argued that God does not play dice with the universe, expressing discomfort with the randomness implied by quantum theory. But Bohr countered that the randomness was not a flaw. It was a fundamental aspect of nature. His debates with Einstein became legendary, representing a clash between two worldviews, one rooted in classical determinism and the other embracing the new quantum reality. Bohr maintained that physics must describe what can be observed and measured, not what classical intuition demands. This philosophical stance guided the development of quantum mechanics and helped stabilize the theory during its formative years. Without Bohr's intellectual clarity and his willingness to challenge even the greatest minds, the quantum revolution might have stalled or taken a very different direction. Beyond its philosophical impact, Bohr's atomic model revolutionized the practical understanding of atoms in ways that paved the path for modern technology. In classical physics, the atom was a mechanical system with predictable motion, but this view could not explain chemical reactions, electrical conductivity, or the behavior of materials at the microscopic scale. With Bohr's quantized model, scientists gained a new understanding of how electrons populate different energy levels and how these distributions determine the chemical and physical properties of elements. The periodic table suddenly made deeper sense: why certain elements behaved similarly, why some formed bonds while others remained inert. All of these patterns related directly to quantized electron configuration. The idea that electrons filled discrete shells, each with a fixed capacity, allowed chemists and physicists to explain atomic interactions in a unified way that had never been possible before. This quantized view of atomic structure became the foundation for the fields of spectroscopy, quantum chemistry, semiconductor physics, and countless others. Every time an engineer designs a microchip, every time a physicist studies electron transition in materials, and every time a chemist explains molecular bonding, Bohr's influence is present. His model unlocked a level of understanding that became essential for developing the technologies that power the modern world. From LED lights to MRI machines, from atomic clocks to quantum computers, the principles established by Bohr's quantum idea permeate the engines of innovation that drive human progress today. His work may have begun as a theoretical attempt to solve a puzzle, but it ultimately reshaped the fabric of society in ways Bohr himself could never have anticipated. The transformation Bohr brought to physics also changed the way scientists approached the unknown. Before Bohr, many believed that classical laws could be stretched or refined to explain everything. But Bohr demonstrated that there are limits to classical reasoning. When dealing with the microscopic world, entirely new principles are required. This realization encouraged scientists to pursue bold hypotheses, to question assumptions, and to explore the boundaries of the possible. It shifted the culture of scientific inquiry from one of strict adherence to classical intuition to one that embraced abstraction, probability, and mathematical formalism. Bohr's success proved that new ideas, no matter how radical, could overturn centuries of established knowledge if they explained nature more accurately. In the years that followed, Bohr became a central figure in the quantum community, mentoring young physicists, guiding discussions, and shaping the philosophical foundations of the new science. His institute in Copenhagen became a hub of intellectual activity, attracting some of the greatest minds of the 20th century. There, the next generation of quantum physicists refined the theories that govern everything from atomic nuclei to subatomic particles. Bohr's influence extended far beyond his own discoveries. He cultivated an environment where innovation flourished, where ideas collided, and where the future of physics took shape. Yet the true measure of Bohr's contribution lies not only in the theories themselves, but in the shift in worldview they required. The notion that the atom is stable because electrons occupy quantized orbits is now so familiar that it seems almost obvious, but at the time, it was an audacious break from established thought. It forced physicists to accept that nature behaves fundamentally differently at microscopic scales. It required a complete rethinking of energy motion and the relationship between matter and light. Bohr's model became the point at which science stepped into the quantum world, a world that was strange, unpredictable, and deeply counterintuitive, yet profoundly real and incredibly powerful. As modern physics continues to advance, Bohr's legacy remains at its core. His quantum idea laid the foundation for theories that now explore the farthest edges of reality, from the behavior of particles in accelerators to the entanglement phenomena used in quantum communication. The stability of atoms, once an unsolvable riddle, is now understood as a natural consequence of quantized energy levels. What was once a radical idea is now a fundamental truth woven into every branch of physics. Bohr's willingness to trust the mathematics of his model over the expectations of classical intuition opened the door to a new understanding of the universe, one that continues to reveal deeper layers of complexity and beauty. In the end, Bohr's revolutionary atomic model did more than transform modern physics. It changed humanity's relationship with the invisible world within matter. It showed that the universe is not merely a mechanical clockwork, but a tapestry of quantized energies, dynamic probabilities, and elegant mathematical patterns. It taught scientists to question, to adapt, and to remain open to new ways of interpreting reality. And it ensured that Niels Bohr's name would forever be etched into the story of science as the visionary who helped unlock the quantum nature of the universe. The idea of quantized electron orbits stands as one of the most daring conceptual leaps in the history of physics, a leap that reshaped our understanding of matter down to its deepest foundation. Before this idea emerged, scientists were trapped in a paradox the atom, the building block of everything, could not be explained by the existing laws of physics. Classical theories predicted that atoms should be unstable, that electrons should spiral into the nucleus within a fraction of a second, releasing radiation continuously until the entire atomic structure collapsed. Yet the world around us was stable. Atoms did not collapse. Matter held its form. Something was profoundly missing in the classical picture, and for decades, physicists could not find the key. The path to solving this paradox began with a series of discoveries that slowly chipped away at classical assumptions. Spectral lines, for example, had been observed for years. Precise, sharp frequencies of light emitted by elements such as hydrogen. These lines were measured with extreme accuracy, yet their origin remained a mystery. Classical physics suggested that atoms should emit a continuous range of wavelengths as electrons decayed gradually, but experiments showed only distinct, sharply defined lines. It was as though atoms communicated in a secret code, emitting only certain notes while ignoring all the others. The question that haunted physicists was simple yet profoundly unsettling. Why were atoms so selective? What determined these specific wavelengths? Why was nature so precise? The answer began to take shape when Niels Bohr dared to break from the classical world entirely. Influenced by Max Planck's proposal that energy was quantized, Bohr wondered if electrons inside atoms might also obey a quantized rule, one that allowed them to occupy only specific orbits with fixed energies. Instead of moving freely through a continuous range of paths around the nucleus, perhaps electrons were restricted to certain allowed states. Like rungs on a ladder, they could not exist between these rungs. They could only jump from one to another by absorbing or emitting discrete amounts of energy. Such a picture was radical, defying every known rule of motion, yet it offered a possible explanation for the mysterious spectral lines. If each electron transition released light with a frequency corresponding to the energy difference between two allowed orbits, then the spectral lines would no longer be mysterious, they would be the signatures of quantum jumps. To understand the significance of this idea, one must appreciate how deeply classical physics was ingrained in scientific thinking. For centuries, physicists believed that energy varied smoothly and continuously, that the world behaved predictably according to well-defined laws. The notion that electrons might be forbidden from occupying certain energies was almost unthinkable. But Bohr was willing to embrace the unthinkable because the evidence demanded it. The spectral lines of hydrogen lined up perfectly with the mathematical predictions of his quantized orbits. What classical theories could not explain in decades, Bohr's idea explained elegantly and immediately. It was as though he had found the master key that unlocked the structure of the atom. The introduction of quantized orbits also solved the stability problem that had overwhelmed classical physicists. In the new quantum picture, electrons in certain allowed orbits did not radiate energy at all. They remained stable, circling the nucleus without losing energy, even though classical theory predicted that they must. This single assumption overturned centuries of established thought. According to Bohr, electrons radiated energy only when they changed orbits, not while they remained in them. This meant that atomic structure was inherently stable, not because classical forces were balanced, but because quantum rules prevented collapse. The quantization of energy acted like a protective barrier, ensuring that electrons could not simply fall into the nucleus. They were anchored to specific states, and these states were the reason atoms endured. Bohr's idea also offered insight into why atoms of different elements produced different spectral patterns. Each element had its own arrangement of allowed energy levels, determined by its number of electrons and the structure of its nucleus. Hydrogen, with its single electron, produced the simplest pattern. More complex atoms produced richer, more intricate spectra. The atomic fingerprint of every element was no longer a mysterious phenomenon. It was a direct map of the quantum structure of its electron orbits. This not only confirmed Bohr's model, but also opened new paths in astronomy, chemistry, and material science. By studying spectral lines from distant stars, scientists could now identify elements present in objects millions of light years away. The universe began to reveal its chemical secrets because Bohr had revealed the quantum structure of the atom. The impact of quantized electron orbits went far beyond explaining spectral lines. It initiated a fundamental change in scientific philosophy. For centuries, physicists believed that the universe operated like a giant machine, with every part behaving predictably. But Bohr's model introduced a new kind of behavior that did not follow classical intuition. Electrons did not move gradually from one orbit to another, they leapt instantaneously. They did not radiate energy continuously. They emitted it in bursts of specific sizes. The continuity that classical physics took for granted was shattered. In its place emerged a new world where nature chose only certain energy states, where discreteness replaced smooth variation, and where unseen rules shaped the foundations of matter. This new philosophy required scientists to reinterpret everything they thought they knew about atomic structure. The atom was no longer a miniature solar system. It was a quantized entity, governed by mathematical constraints that had no classical analog. The idea of quantized orbits changed not only physics but also how scientists viewed the relationship between mathematics and nature. Instead of expecting nature to follow intuitive physical rules, scientists began to accept that the universe might operate according to abstract mathematical principles, even if they defied common sense. Bohr's model was a victory of mathematics over intuition, of abstraction over classical experience. This shift in perspective laid the foundation for the development of quantum mechanics. Werner Heisenberg, for instance, took Bohr's ideas and transformed them into matrix mechanics, a highly mathematical framework that treated electron transitions as fundamental events. Erwin Schrödinger later introduced wave mechanics, offering a more visual interpretation that described electrons as wave-like entities spread out across space. Both approaches, though different in form, relied on the same core idea: electrons inhabit quantized states. The mathematical framework of quantum mechanics might have grown far beyond Bohr's original picture, but the idea of quantization remained central. Every equation, every model, every interpretation of the quantum world depended on the notion that electrons cannot exist at arbitrary energies. Even today, the concept of quantized electron orbits remains one of the pillars of modern science. It forms the basis of quantum chemistry, determining how atoms bond, how molecules form, and how materials behave. It explains why metals conduct electricity, why semiconductors behave differently, and why insulators resist current. It governs the function of lasers, the operation of LEDs, and the principles behind quantum computing. Every modern technology that involves electrons, whether it is a smartphone chip, a solar panel, a magnetic resonance imager, or a quantum sensor, depends on the rules set forth by Bohr's quantization of electron orbits. Yet the true beauty of Bohr's idea lies not just in its applications, but in its simplicity. The concept that electrons occupy only certain allowed states, simple as it seems, captured a profound truth about the universe. Nature is not arbitrary or chaotic. It follows elegant rules hidden beneath the surface of visible reality. The quantization of electron orbits revealed that the universe has a structure deeper than classical theories could ever describe. It showed that even the smallest particles obey laws that are consistent, precise, and fundamentally mathematical. The story of quantized electron orbits continues beyond the initial revelation, extending into a profound transformation in how scientists interacted with the very concept of measurement, prediction, and the limits of human understanding. Once Bohr introduced the idea that electrons could occupy only specific orbits, the scientific community began to confront deeper questions. What determines these allowed orbits? How does an electron make its sudden jump from one orbit to another? What does it even mean for an electron to be in an orbit if its motion cannot be described by classical paths? These questions did not weaken Bohr's idea. They pushed physics into an entirely new domain that demanded more powerful theories, more refined experiments, and a willingness to accept that the universe was stranger than anyone imagined. As researchers studied the quantized structure of the atom more deeply, they realized that the classical image of electrons orbiting like planets around the sun could no longer be sustained. It was a helpful picture for beginners, but fundamentally inaccurate. The electron was not a miniature planet obeying Newton's laws. It was a quantum object whose behavior depended on probability, uncertainty, and wave-like characteristics. The quantized orbit was not a physical circular path, but a stable energy condition, a mathematical state where the electron could exist without radiating energy. What Bohr had done was capture the overall pattern of atomic stability and spectral emission, even though the details of electron motion needed rethinking. This realization opened the door for a deeper, more abstract model of atomic structure, one that would soon be provided by the wave mechanics of Schrödinger. But before that revolution occurred, the scientific community needed reassurance that quantized orbits were not a mathematical trick, but a real feature of nature. Experiments soon provided overwhelming support. When atoms were subjected to strong magnetic fields, their spectral lines split in ways that precisely matched predictions based on quantized electron states. This phenomenon, known as the Zeeman effect, had previously baffled classical theorists. But with Bohr's quantized framework, it became understandable. The electron's energy levels were sensitive to magnetic influences, and these influences changed the allowed states in predictable ways. Each split line was a whisper from the electron, revealing its quantized identity. The more physicists pushed atoms with external forces, the more atoms responded in ways that affirmed quantization. Nature was not continuous at the smallest scales. It was a staircase, where electrons stood only on certain steps and never between them. As more experiments confirmed the truth of quantized electron states, the scientific mindset began to change. A new generation of physicists grew up in a world where the quantum nature of atoms was a given, not a controversy. The idea that electrons had allowed orbits became the starting point for further exploration rather than a radical departure. It shaped how researchers approached unsolved problems, encouraging them to think in terms of discrete quantities rather than continuous ones. This shift in thinking proved essential when scientists confronted the mysteries of chemical bonding. Classical theories could not explain why atoms bonded the way they did, why molecules formed at specific angles, or why some elements were highly reactive while others were almost inert. But with the concept of quantized electron states, these mysteries began to unravel. Bonding became a story of electrons occupying shared or overlapping quantum states. Reactivity became a question of how easily electrons could transition to new allowed states. Inertness emerged from tightly filled shells where no more stable states were available for bonding. Thus, Bohr's simple idea became the backbone of chemistry. It guided the development of periodic table theory, explaining why elements in the same column behave similarly. It revealed why noble gases resist chemical reactions. They had filled electron shells that left no room for additional electrons. It clarified why alkali metals were so reactive they had a single loosely bound electron ready to leap into a new state during bonding. The entire structure of chemical science, once a catalogue of empirical observation, now had a logical foundation rooted in quantized electron behavior. This transformation elevated chemistry from a descriptive science to an explanatory one, bridging it with physics at a fundamental level. Even as chemistry flourished under the influence of quantized orbits, physics itself continued to feel the impact. The atom was no longer a mysterious black box. It had become a playground for exploring fundamental principles, and Bohr's idea served as the guiding framework. When scientists probed atoms with high-energy particles, they discovered that transitions between energy levels occurred at lightning speed, far faster than any classical motion could account for. These instantaneous transitions, quantum jumps, became one of the most controversial features of quantum behavior. How could an electron disappear from one orbit and reappear in another without passing through the space in between? Bohr defended the idea, insisting that quantum transitions were not classical trajectories, but fundamental events governed by rules beyond classical logic. These quantum jumps later became the foundation of technologies such as lasers, where electrons are forced to accumulate in excited states and then release energy in synchronized bursts. Every new discovery reinforced the idea that quantized electron states were not just a convenient mathematical construct, but the actual architecture of the microscopic world. This led to a deeper philosophical realization. Nature is quantized at its core. It does not allow arbitrary amounts of energy, nor does it permit arbitrary forms of motion. Instead, it operates through discrete units, packets of energy, packets of momentum, packets of angular momentum. The entire universe seemed to be built upon quantized frameworks, not continuous gradients. This idea was so completely at odds with classical physics that many scientists struggled to accept it. Yet the evidence was undeniable, and as time passed, quantization became a foundational principle of scientific understanding. The story did not end with the atom. Quantized electron states played a crucial role in the development of solid-state physics. the field that explains how electrons behave in crystals, metals, semiconductors, and insulators. In solids, electrons occupy bands, ranges of allowed energies separated by forbidden gaps. This band structure emerged directly from the idea that electron states are quantized. It is why metals conduct electricity. They have electrons in energy bands that allow free movement. It is why insulators do not conduct. Their electrons are trapped in filled bands with no available state. It is why semiconductors behave uniquely. They have carefully spaced bands that allow controlled conduction under the right conditions. All of modern electronics, transistors, computer chips, LED screens rests upon the band structure of materials, which itself originates from the quantization of electron energy levels. With the rise of quantum mechanics, the language of quantized orbits evolved into a more abstract vocabulary: wave functions, orbitals, probability densities. Electrons were no longer thought of as particles following circular paths, but as cloud-like distributions obeying mathematical equations. Yet even as the interpretation changed, the underlying principle remained the same. Electrons could occupy only certain allowed energy states. Bohr's orbits transformed into Schrödinger's wave functions, but the quantization survived. It became the bridge between old quantum theory and the fully developed quantum mechanics that dominated 20th century physics. It was the thread that connected the early struggles of atomic theory to the triumphs of modern science. As quantum mechanics matured, Bohr's influence continued to shape not just scientific theories, but the very philosophy of physics. He championed the idea that the act of measurement played a crucial role in defining the properties of quantum systems. Without observation, the electron could not be said to occupy any specific location or state. It existed only as a range of possibilities, constrained by the quantized rules governing its behavior. This idea, controversial as it was, laid the groundwork for the Copenhagen interpretation of quantum mechanics, a perspective that dominated 20th century physics and continues to influence scientific thinking today. It suggested that the quantum world is fundamentally different from the classical world, and that attempts to understand atomic behavior through classical concepts would always fall short. In the modern era, the concept of quantized electron states continues to drive innovation. Quantum computing, for example, relies on manipulating the quantum state of particles, allowing them to exist in multiple states simultaneously. Quantum sensors exploit the sensitivity of quantized energy levels to detect tiny changes in fields or forces. Quantum communication uses controlled electron transitions to create secure channels based on the laws of quantum entanglement. Each of these technologies depends on the idea that electrons exist in discrete quantum states, a direct descendant of Bohr's revolutionary insight. The legacy of quantized orbits does not lie in the circular diagrams still found in textbooks, but in the vast tapestry of physics, chemistry, and technology woven from the thread Bohr first pulled. In the end, the concept of quantized electron orbits remains one of the most influential ideas in the history of science. It reshaped our understanding of matter, gave birth to quantum mechanics, unified physics with chemistry, and laid the foundation for the technological world of today. It revealed that the universe is not a continuous gradient, but a symphony of discrete notes, each one corresponding to a specific quantum state. Bohr's vision allowed humanity to see the atom not as a chaotic mystery, but as an ordered, structured system governed by precise rules. This shift transformed the entire landscape of science, ensuring that the concept of quantized electron orbits would forever stand as one of the great pillars of modern physics. The story of Niels Bohr's influence on quantum thinking cannot be told without examining the profound impact that his work drew from the insights of Max Planck and Ernest Rutherford. Bohr did not create his revolutionary atomic model in isolation. It was the product of a scientific lineage that had begun to crack open the mysteries of matter and energy. Planck had already proposed the radical idea that energy is quantized, a notion so counterintuitive that even the most imaginative physicists struggled to grasp it fully. Energy, he suggested, was not a smooth continuum, but existed in discrete packets, quanta, each with a precise magnitude determined by frequency. This concept had initially been introduced to solve the problem of black-body radiation, a technical issue regarding the emission of light from heated objects, yet its implications were far greater than Planck might have imagined. It implied that the very fabric of reality at microscopic scales was discontinuous, that nature operated not through smooth gradients but through jumps and increments. At the same time, Ernest Rutherford had revolutionized the understanding of atomic structure through his groundbreaking gold foil experiment. By bombarding thin sheets of gold with alpha particles, Rutherford revealed that most particles passed through without deflection, while some rebounded sharply. This observation shattered the earlier plum-pudding model of the atom, which imagined electrons embedded uniformly in a positively charged sphere. Instead, Rutherford proposed the atoms consist mostly of empty space with a dense, positively charged nucleus at the center. This nuclear model provided the first glimpse of a structured atom, but it left unanswered questions. According to classical physics, electrons orbiting the nucleus should continuously emit radiation, losing energy and spiraling into the nucleus. Atoms, by these laws, should not exist. Yet they did, and the universe remained stable. This paradox became the central puzzle that would occupy Bohr and ultimately define his contribution. Bohr's genius was his ability to synthesize these disparate ideas into a cohesive framework. He recognized that the discrete energy levels suggested by Planck's work could resolve the stability problem identified by Rutherford's nuclear model. If electrons were restricted to specific allowed orbits, they could maintain stable configurations without radiating energy continuously. The concept of quantization was not merely a mathematical trick but a real principle governing the structure of atoms. Bohr's insight was that these orbits, or stationary states, provided the scaffolding necessary to reconcile the experimental evidence with theoretical reasoning. By imposing quantum rules onto Rutherford's atom, Bohr created a model that explained stability, spectral lines, and the fundamental architecture of matter in one elegant framework. What made this synthesis particularly remarkable was the audacity of the assumptions involved. Electrons were no longer classical particles obeying Newtonian dynamics. They were quantum entities constrained by discrete energy levels. Their transitions from one orbit to another, which emitted or absorbed light, occurred instantaneously rather than gradually. This challenged centuries of intuition about motion and energy. Yet Bohr's model was supported not just by abstract reasoning but by empirical success. When applied to hydrogen, the simplest atom, it precisely predicted the spectral lines that had mystified scientists for decades. Convergence of theory. An experiment validated Bohr's daring assumptions and elevated him to a position of profound influence in the emerging field of quantum mechanics. The influence of Planck on Bohr went beyond the specific concept of energy quantization. Planck's approach demonstrated the power of mathematics to reveal underlying truths about nature that were not accessible to direct observation. Bohr internalized this lesson, understanding that atomic behavior could be governed by rules invisible to the naked eye, but apparent through careful mathematical reasoning. He realized that to explain the atom, one had to accept principles that contradicted everyday experience. This willingness to embrace abstract, counterintuitive concepts became a hallmark of Bohr's thinking and laid the groundwork for the intellectual flexibility required in the development of quantum theory. Rutherford's contribution, in turn, provided the physical canvas on which Bohr could paint his quantum ideas. The concept of a dense nucleus at the center of an atom offered a focal point around which electrons could orbit. But it was only Bohr's application of quantum rules that made these orbits stable and predictive. The interplay between Planck's abstract quantization and Rutherford's empirical nuclear model created a synergy that allowed Bohr to construct a new understanding of atomic structure. Neither insight alone could have produced the Bohr model. It was their combination that transformed atomic theory and established a foundation for all subsequent developments in quantum mechanics. Bohr's model also introduced a profound connection between matter and light. Classical physics could not explain why atoms emitted light in discrete frequencies rather than a continuous spectrum. By incorporating quantized orbits, Bohr demonstrated that light is emitted or absorbed only when electrons transition between specific energy levels. Each quantum jump corresponds to a precise photon of light, linking the atom's internal structure directly to observable electromagnetic radiation. This not only resolved a long-standing empirical puzzle, but also reinforced the principle that nature at its smallest scales operates according to discrete, predictable rules. The harmony between quantized atomic orbits and the properties of light underscored the elegance and power of Bohr's synthesis, showing that quantum ideas could unify seemingly unrelated phenomena. The broader implications of Bohr's synthesis extend beyond atomic physics. By combining Planck's quantum hypothesis with Rutherford's nuclear model, Bohr demonstrated a methodology that would become central to scientific inquiry: the integration of theoretical insight with experimental evidence. Bohr's approach emphasized that successful theories must not only be internally consistent but also capable of explaining observation. This principle guided future developments in quantum mechanics and became a benchmark for evaluating new scientific ideas. Bohr showed that it was possible to push beyond classical limitations without losing contact with empirical reality, a balance that remains a cornerstone of modern physics. Bohr's work also inspired a generation of physicists to think in new ways about the microscopic world. His model suggested that classical intuitions about motion, energy, and stability were insufficient at atomic scales. This intellectual shift encouraged physicists to explore abstract concepts such as wave-particle duality and quantum superposition, which would later become central to the full formulation of quantum mechanics. By demonstrating that nature could behave in fundamentally non-classical ways, Bohr opened the door to a universe governed by rules that transcended ordinary experience. And he did so with a model that was both conceptually clear and mathematically precise. The influence of Planck and Rutherford on Bohr also underscores the cumulative nature of scientific progress. Each discovery built upon previous work, forming a chain of insights that converged in the Bohr model. Planck provided the theoretical framework of quantization. Rutherford provided the empirical understanding of nuclear structure, and Bohr synthesized these insights to solve a long-standing puzzle about atomic stability. This chain of influence illustrates how scientific revolutions often emerge not from isolated genius alone, but from the interplay between ideas, experiments, and the broader intellectual context. Bohr's ability to integrate these influences demonstrates both his brilliance and his understanding of science as a collaborative, evolving enterprise. The success of Bohr's model in explaining the hydrogen spectrum further cemented the importance of these influences. The discrete lines of hydrogen could now be understood as the direct consequence of quantized electron transition between orbits, defined by Bohr's application of Planck's energy quanta to Rutherford's nuclear atom. This not only validated Bohr's approach but also provided a clear example of how theory and experiment could reinforce one another. The ability to predict observable phenomena from theoretical principles represented a significant advance in scientific methodology, and it established Bohr as a central figure in the development of quantum theory. Bohr's synthesis of Planck and Rutherford also had profound philosophical implications. It challenged the notion that classical physics could fully describe all natural phenomena and suggested that the universe operates according to discrete, quantized principles at fundamental scales. This required scientists to rethink concepts of continuity, determinism, and causality. Bohr's approach demonstrated that progress in understanding nature sometimes demands a radical reimagining of foundational concepts. The willingness to adopt counterintuitive principles in the face of empirical evidence became a defining feature of modern physics, and it remains a guiding principle for scientific exploration today. At the same time, Bohr's work exemplified the interplay between mathematical reasoning and experimental verification. Planck's quantization provided the mathematical tool, Rutherford's nuclear model provided the physical reality, and Bohr's insight demonstrated how these elements could be integrated to produce testable predictions. This balance between theory and experiment became a hallmark of quantum physics, guiding the work of Heisenberg, Schrödinger, Dirac, and others as they developed the full framework of quantum mechanics. Bohr's approach showed that even the most abstract ideas must ultimately confront empirical reality, and that the most powerful scientific theories are those that successfully bridge this gap. Bohr's synthesis of Planck and Rutherford did more than provide a successful atomic model, it transformed the very methodology of physics. Before Bohr, theories often relied heavily on intuition drawn from macroscopic experience. Planets orbited stars in predictable paths, pendulums swung with precise timing, and forces could be visualized as pushes or pulls in space. This worldview led physicists to expect that electrons, too, should behave like miniature planets orbiting a nucleus in continuous paths. Bohr shattered that expectation. By applying Planck's principle of quantized energy to Rutherford's nuclear atom, he demonstrated that the rule governing the microscopic world could be fundamentally different from those governing the macroscopic world. Nature, he showed, could be discrete and probabilistic, and yet still consistent and predictable in its own terms. This intellectual leap required not only technical skill, but a willingness to let go of deeply ingrained assumptions about how the universe must behave. The impact of Bohr's model was immediate and far-reaching. Spectroscopy, the study of the light emitted or absorbed by atoms, suddenly gained a theoretical foundation. The mysterious lines in the hydrogen spectrum, which had perplexed scientists for decades, now had a clear explanation. Each line corresponded to a photon emitted or absorbed when an electron jumped between allowed orbits. This explanation was not only mathematically precise, but also experimentally verifiable. The energy differences calculated from Bohr's model matched the observed spectral lines exactly. The agreement between theory and experiment provided compelling evidence for the correctness of the quanti-orbit hypothesis and demonstrated the power of combining abstract principles with empirical data. It was a triumph that reinforced the importance of both Planck's and Rutherford's contribution, showing that revolutionary ideas often emerge from the interplay of multiple scientific insights. Bohr's atomic model also illuminated the role of the nucleus in determining atomic behavior. Rutherford had shown that the nucleus contained almost all the mass of the atom, but the significance of this concentration of positive charge became clearer when combined with Bohr's quantized orbits. The nucleus was not simply a passive core. Its charge dictated the energy levels available to orbiting electrons. The stronger the nuclear charge, the more tightly electrons were bound, and the greater the energy difference between allowed orbits. This insight provided a unifying framework for understanding not only hydrogen but also more complex atoms. The principles laid down by Bohr allowed scientists to explore multi-electron systems, laying the groundwork for the periodic table's theoretical explanation, and ultimately enabling the prediction of chemical behavior from first principles. The integration of Planck's and Rutherford's ideas into Bohr's model also led to profound philosophical implications regarding the nature of reality. Planck's quantization implied that energy changes occur in discrete units, challenging the classical notion of continuity. Rutherford's nuclear atom suggested a structural hierarchy at the heart of matter, contradicting older ideas of uniformity and homogeneity. Bohr combined these insights to propose that atoms are governed by rules that differ fundamentally from our everyday experiences. Electrons, constrained to discrete energy levels, do not radiate energy arbitrarily but only during specific transitions. This departure from classical mechanics required scientists to reconsider the meaning of motion, energy, and stability. The quantum atom revealed a world where intuition must be supplemented or even replaced by careful theoretical reasoning and empirical verification. Bohr's approach exemplified a balance between abstraction and observation. He did not discard physical reality in favor of mathematical formalism, nor did he rely solely on observation without theoretical guidance. Instead, he synthesized the strengths of both Planck's abstract quantization and Rutherford's empirical nuclear model. This methodological innovation became a hallmark of quantum mechanics. Theories must be internally consistent, mathematically rigorous, and capable of explaining experimental phenomena. Bohr's synthesis demonstrated that revolutionary advances often require bridging the gap between conceptual innovation and empirical validation. It was this very bridge that allowed the Bohr model to gain rapid acceptance. Despite its radical departure from classical expectations, the influence of Bohr's model extended into the rapidly developing field of quantum theory. Scientists such as Werner Heisenberg and Erwin Schrödinger expanded on Bohr's insights, developing matrix mechanics and wave mechanics respectively. Heisenberg's formulation emphasized the quantization of observable properties, while Schrödinger's approach treated electrons as wave functions spread across space. Yet both retained the core principle that electrons occupy discrete energy states. Bohr's integration of Planck and Rutherford provided the conceptual foundation for these developments, illustrating how discrete energy levels arise from the interplay of nuclear forces and quantum principles. Without this synthesis, the path to a complete quantum mechanics would have been far less clear. The unification of atomic theory and quantum principles might have taken much longer to achieve. Bohr's model also highlighted the importance of considering both micro and macroscopic perspectives. While classical physics described motion at human scales with continuous variables, the quantum world behaved differently. Bohr's work emphasized that principles applicable at one scale might not hold at another, a realization that remains central to physics today. The ability to navigate between scales, to recognize where classical approximations break down and where quantum principles dominate, is a direct intellectual legacy of Bohr's synthesis. It taught scientists to approach nature with humility, acknowledging that observable phenomena are only one aspect of a complex, multi-layered reality. The explanatory power of Bohr's model extended beyond physics into chemistry, material science, and emerging technologies. Quantized energy levels explained chemical reactivity, the formation of bonds, and the stability of molecules. Electrons in defined orbitals accounted for the structure of the periodic table and clarified trends in elemental behavior. The same principles guided the development of semiconductors, lasers, and magnetic resonance imaging, connecting abstract quantum theory to practical applications that shape modern life. Each of these advances traces its roots back to the foundational idea that Planck's energy quantum and Rutherford's nuclear structure could be integrated into a coherent model of the atom. Furthermore, Bohr's work exemplified the collaborative and cumulative nature of scientific progress. His model would not have been possible without Planck's quantization or Rutherford's nuclear experiment, and in turn, it provided a platform for future physicists to extend and refine atomic theory. Scientific breakthroughs rarely occur in isolation. They emerge from the dialogue between theory and experiment, between imagination and observation. Bohr's synthesis illustrates how ideas build upon one another, how revolutionary insights often arise at the intersection of multiple lines of inquiry, and how the scientific enterprise advances through cumulative understanding rather than isolated genius alone. Bohr's ability to integrate these influences also had a lasting impact on the philosophy of science. It demonstrated that scientific progress requires both bold conceptual innovation and rigorous engagement with empirical data. The quantum atom, built from Planck's abstract ideas and Rutherford's experimental discoveries, provided a model that was not only mathematically elegant, but also experimentally verifiable. This balance between theory and observation remains a guiding principle for scientific exploration today. Bohr showed that understanding the universe often demands embracing concepts that challenge classical intuition while remaining anchored in evidence. Finally, Bohr's model highlighted the importance of synthesis in advancing knowledge. By uniting Planck's quantum hypothesis with Rutherford's nuclear model, Bohr created a framework capable of explaining atomic stability, spectral lines, and the broader behavior of matter. This synthesis did more than solve a single problem. It transformed the conceptual landscape of physics, setting the stage for the development of modern quantum mechanics. Bohr demonstrated that scientific breakthroughs often emerge from the ability to connect seemingly disparate ideas, to see patterns where others see only complexity, and to create models that unify theory and experiment in a coherent whole. Bohr's achievement is therefore a testament to the power of intellectual integration. He took the discrete, mathematical insights of Planck and the empirical, structural observations of Rutherford, and wove them into a revolutionary model that forever changed our understanding of the atom. This synthesis exemplifies the creative and cumulative nature of scientific discovery, showing how profound ideas arise from the dialogue between theory and experiment, between abstraction and observation. In doing so, Bohr not only advanced atomic physics, but also reshaped the methodology, philosophy, and scope of science itself, leaving a legacy that continues to influence the pursuit of knowledge in countless fields today. Bohr's exploration of the quantum idea that made him a legend cannot be fully understood without examining the profound impact of the correspondence principle, a concept that bridged the classical and quantum worlds. In the early 20th century, classical physics reigned supreme, describing motion, energy, and electromagnetic phenomena with remarkable accuracy at macroscopic scales. Yet, at the atomic level, These same laws produced paradoxes. Electrons orbiting a nucleus, according to classical physics, should radiate energy continuously, spiral into the nucleus, and cause atoms to collapse almost instantly. The universe clearly was stable, suggesting that classical laws were insufficient to explain the microscopic domain. Bohr recognized that a new principle was needed, one that could reconcile the novel rules of the quantum world with the familiar patterns of classical physics. The correspondence principle was Bohr's answer to this challenge. It stated that the behavior of systems described by quantum mechanics must approximate classical physics in the limit of large quantum numbers or high energies. In essence, while electrons in small orbits obeyed quantum rules, as orbits became larger and energies higher, the results should converge to the predictions of classical physics. This principle provided a conceptual bridge between two seemingly incompatible frameworks: the continuum, deterministic world of classical mechanics and the discrete, probabilistic domain of quantum mechanics. By insisting that quantum theory must respect classical expectations in the appropriate limit, Bohr ensured that his revolutionary ideas remained grounded in physical reality, preventing them from drifting into pure abstraction or speculative fantasy. The correspondence principle also guided the practical application of Bohr's atomic model. For the hydrogen atom, it explained why the quantized energy levels produced discrete spectral lines while still connecting with classical predictions at high quantum numbers. Transitions between closely spaced energy levels in large orbits closely mimicked the continuous radiation predicted by classical physics. This allowed physicists to see continuity emerging naturally from the underlying quantum framework, reassuring them that the strange rule of the microscopic world did not violate the observed behavior of larger systems. In this way, Bohr's principle provided both a predictive tool and a philosophical anchor, demonstrating that quantum theory was not an isolated anomaly but a deeper layer of physical law consistent with classical experience. Beyond its technical application, the correspondence principle had a profound impact on scientific thinking. It introduced the idea that new theories do not entirely discard old ones, but rather extend and refine them, providing more general explanation. Classical physics was not rendered obsolete. It became a limiting case of a more complete quantum theory. This perspective reshaped how scientists approached theoretical innovation, encouraging them to seek connection and continuities between old and new frameworks, rather than rejecting established knowledge outright. Bohr's approach exemplified the balance between radical innovation and conceptual continuity that defines the most enduring scientific breakthroughs. The principle also played a crucial role in the broader development of quantum mechanics. It influenced the work of Heisenberg, Schrödinger, and Dirac as they formulate matrix mechanics, wave mechanics, and relativistic quantum theory. In each case, the correspondence principle provided a guideline. New formulations of quantum behavior must reproduce classical results when quantum effects become negligible. This constraint ensured that the emerging theory remained physically meaningful and experimentally testable, fostering confidence in the counterintuitive and abstract formulations of early quantum physics. It also highlighted Bohr's insight that the coherence of theory and observation is as important as mathematical elegance. In addition to its methodological and philosophical significance, the correspondence principle deepened the understanding of atomic structure. It suggested that quantized energy levels were not arbitrary inventions but reflections of underlying physical laws that naturally connected to classical dynamics at appropriate scales. Electrons did not behave randomly. Their discrete states were part of a continuum, a spectrum of possibilities extending toward classical predictions. This understanding helped scientists visualize the transition between quantum and classical domain, providing an intuitive framework for imagining atomic behavior in both small and large systems. It also emphasized the elegance and universality of physical laws, revealing how seemingly separate phenomena, microscopic jumps and macroscopic motion, are interconnected within a coherent theoretical structure. Bohr's use of the correspondence principle also had implications for interpreting experimental data. By recognizing that quantum and classical predictions converge in certain limits, physicists could design experiments that tested quantum predictions while remaining consistent with classical expectations. Spectroscopy, for example, benefited from this insight, as the spacing of spectral lines could be related to classical orbital frequencies in high-energy states. The principle offered a bridge between measurement and theory, guiding experimentalists in identifying patterns and regularities in atomic behavior. It became a tool not only for prediction but also for interpretation, enhancing the power of quantum theory to explain and anticipate natural phenomena. Finally, the correspondence principle illustrates Bohr's broader intellectual vision. It reflects his belief in the harmony of the universe, where new discoveries extend rather than contradict existing knowledge. By connecting the quantum and classical worlds, Bohr demonstrated that innovation does not require abandoning tradition. Rather, it requires finding the underlying unity that reconciles new insights with established understanding. The principle is a testament to Bohr's ability to navigate complexity, balance abstraction with reality, and synthesize diverse strands of knowledge into a coherent framework. It is a critical aspect of why Bohr's contributions endure. His ideas were not only revolutionary, but also intellectually rigorous, philosophically profound, and experimentally grounded. In conclusion, the correspondence principle was a cornerstone of Bohr's quantum thinking. It provided a conceptual bridge between classical and quantum physics, guided practical applications of the atomic model, influenced the development of quantum mechanics, and shaped the philosophical approach to scientific innovation. By insisting on continuity between new theories and established observations, Bohr ensured that his revolutionary idea remained connected to reality, providing both a predictive tool and a philosophical foundation for modern physics. This principle exemplifies the intellectual clarity, methodological rigor, and visionary insight that made Niels Bohr a legendary figure in the history of science, cementing his role as a pioneer who transformed our understanding of the microscopic world. Bohr's exploration of the quantum idea that made him a legend is deeply intertwined with the concept of electron transitions and the emission of light, a phenomenon that revealed the discrete beauty of atomic behavior. Classical physics had long assumed that electrons orbiting the nucleus would emit radiation continuously as they accelerated in their paths, leading to a gradual loss of energy and inevitable collapse of the atom. This posed a paradox. If atoms radiated energy in this manner, matter would be unstable, and the universe as we observe it would not exist. Spectral lines observed in experiments such as those from hydrogen were sharply defined and discrete, not continuous, challenging the prevailing classical framework. Scientists were confronted with a fundamental mystery. Why did atoms emit light only at specific frequencies? And what governed these precise emissions? Bohr's insight provided the solution by proposing that electrons occupy only certain allowed energy levels, and that light is emitted or absorbed only when an electron transitions between these levels. In this framework, electrons do not radiate energy while remaining in a stable orbit. Radiation occurs solely during a jump, a quantum leap, from one permitted orbit to another. Each transition corresponds to a photon with energy exactly equal to the difference between the initial and final orbits, a concept that linked the microscopic world of electrons directly to the observable behavior of light. This explanation resolved the long-standing puzzle of spectral lines, connecting theory and experiment in an elegant and predictive manner. The concept of electron transitions illuminated the fundamental discreteness of nature. Energy is not continuous at the atomic scale. It exists in specific quanta. The jumps between orbits highlight the rules that govern microscopic systems, emphasizing that atomic behavior is probabilistic and governed by quantum laws rather than deterministic classical motion. Electrons are constrained by quantized energy states, and these constraints give rise to the observable phenomena of emission and absorption. The precision of spectral lines reflects the exactness of these energy differences, providing a direct measurement of the quantized structure of the atom. Each photon emitted during a transition is a signature of an electron obeying the strict rules of quantum mechanics. Electron transitions also reveal the deep interplay between matter and radiation. When an electron absorbs energy, it moves to a higher allowed state, storing the energy in a quantized form. Conversely, when it falls to a lower state, it releases the exact amount of energy as a photon. This direct exchange illustrates that energy transfer at the atomic level is both discrete and highly regulated. Unlike classical systems, where energy can be lost or gained in arbitrary amounts, quantum transitions are precise, governed by the difference between fixed energy levels. The regularity of these transitions underpins not only atomic stability, but also the predictability of spectroscopic phenomena, demonstrating the profound order inherent in quantum systems. The implications of electron transitions extend beyond atomic physics into practical technology. Lasers, for example, rely on controlled electron transitions to produce coherent light. By manipulating electrons to occupy excited states and then inducing synchronized drops to lower energy levels, lasers generate highly concentrated beams of light with precise frequency and intensity. Similarly, fluorescent materials, LEDs, and other photonic devices exploit the principle that electrons can emit photons during transitions. The quantized nature of these processes, first proposed by Bohr, provide the foundation for much of modern photonics and quantum technology. Each technological application is a direct consequence of understanding how electrons behave when constrained to discrete energy levels. Electron transitions also shape the development of quantum mechanics by demonstrating that classical trajectories are insufficient to describe atomic behavior. The instantaneous jumps between states defied classical intuition, which would require continuous paths and energy loss along the way. Instead, quantum theory revealed a probabilistic landscape, where the likelihood of an electron occupying a particular state could be calculated, but its exact path was undefined. Bohr's model introduced the notion that electrons are not merely particles in motion but quantum entities whose behavior must be described by probabilities and wave functions. These ideas laid the groundwork for later developments in matrix mechanics and wave mechanics, establishing the conceptual framework of modern quantum physics. Moreover, electron transitions provided a measurable connection between theoretical predictions and empirical data. The energy differences between orbits could be calculated using Bohr's formulas, and these predictions matched the observed spectral lines with remarkable accuracy. Hydrogen's spectrum, for example, displayed a series of lines corresponding exactly to transitions between energy levels. This agreement validated the principle of quantized orbits and demonstrated that quantum theory could produce precise, testable predictions. It also offered a method for probing the internal structure of atoms, allowing scientists to infer the arrangement and energies of electrons based on the light they emit or absorb. The phenomenon of electron transitions further illustrated the universality of quantum principles. While initially applied to hydrogen, the same ideas could be extended, with refinements, to more complex atoms and ions. The patterns of light emitted or absorbed by different elements reflected their unique electron configurations, revealing a deep and systematic order underlying chemical diversity. Electron transitions explained not only why elements emit characteristic spectra, but also why their chemical behavior follows predictable trends. This understanding bridged atomic physics and chemistry, showing that quantum rules govern both the structure of matter and its interactions. Finally, electron transitions highlight the elegance and simplicity of Bohr's contribution. By introducing discrete energy states and quantum leaps, Bohr resolved multiple paradoxes simultaneously. He explained atomic stability, the origin of spectral lines, and the connection between matter and radiation. The model provided a clear and intuitive picture of atomic behavior while remaining mathematically precise. It revealed that the seemingly mysterious phenomena of light emission are natural consequences of quantized electron behavior, demonstrating that the universe operates according to simple, underlying rules even in realms far removed from everyday experience. In conclusion, the concept of electron transitions and the emission of light is central to understanding why Bohr became a legend in quantum physics. These transitions illuminate the discrete nature of energy at the atomic scale, reveal the deep connection between matter and radiation, and provide the foundation for modern technologies ranging from lasers to LEDs. They also exemplify the predictive power of quantum theory, showing how theoretical insights can align perfectly with experimental observation. Through the study of electron transitions, Bohr transformed our understanding of the microscopic world, bridging the gap between abstract principles and observable reality, and establishing a legacy that continues to influence both science and technology today. Bohr's quantum ideas gained legendary status not only for explaining atomic structure, but also for introducing the profound concept of quantum jumps and their implications for the understanding of reality. Classical physics had long assumed that all processes in nature were continuous and predictable. Electrons, like planets in a solar system, were expected to move along defined paths, gradually losing energy as they radiated. This assumption led to the paradox of atomic instability. If electrons emitted energy continuously, atoms would collapse in microseconds, and matter as we know it would not exist. The observation of discrete spectral lines, however, suggested that nature at the atomic level did not operate through continuous processes. Bohr's insight was revolutionary. Electrons could occupy only specific energy levels, and transition between these levels occurred instantaneously in what became known as quantum jumps. Quantum jumps challenged the very notion of continuity. In the macroscopic world, we expect objects to move through intermediate states smoothly. If a ball rolls from one point to another, it passes through every position along the way. Electrons, however, behave differently. When an electron absorbs or emits energy, it does not traverse a continuous path between energy levels. Instead, it appears to jump from one allowed state to another, with the energy difference carried away or absorbed as a discrete quantum of light. These jumps are instantaneous and precise, defying the classical notion of motion, and demonstrate that the rules governing the microscopic world are fundamentally different for everyday experience. By proposing this concept, Bohr illuminated a realm of physical reality that had previously been inaccessible to intuition or direct observation. The implications of quantum jumps extend beyond atomic physics into the nature of measurement and observation. The realization that electrons move discontinuously forced physicists to reconsider the role of observation in determining outcomes. If an electron can exist in one energy state and then suddenly appear in another without traversing intermediate states, the act of measurement becomes crucial. Observing or interacting with the electron effectively reveals its state, highlighting the interplay between the observer and the observed in quantum systems. This idea laid the groundwork for the Copenhagen interpretation of quantum mechanics, where measurement and probability are intrinsic to the description of physical phenomena. Bohr's model, therefore, was not merely a description of atomic structure, it was a radical shift in the philosophical understanding of reality at the microscopic level. Quantum jumps also provided a natural explanation for the emission and absorption of light. Classical theories could not account for why atoms emit light at discrete frequencies rather than in a continuous spectrum. Bohr's model resolved this by linking each quantum jump to a specific photon of light, with energy exactly equal to the difference between the initial and final energy levels. This explained the sharp spectral lines observed in experiments such as those of hydrogen and other elements. Each line represents a quantum transition, a discrete event where energy is transferred precisely and predictably. This conceptual framework established a direct and measurable connection between atomic structure and electromagnetic phenomena, providing empirical support for Bohr's revolutionary ideas. The concept of quantum jumps further underscores the importance of energy quantization. Classical mechanics allows energy to vary continuously, yet atomic behavior demonstrates that only specific energy values are permissible. Quantum jumps are the manifestation of this principle. Electrons cannot occupy arbitrary energies but must reside in allowed states. The exactness of these states explains why spectral lines are sharp and reproducible, and why atoms remain stable. Without the notion of quantum jumps, the precision of atomic emissions would remain inexplicable, and the foundational principles of quantum mechanics would lack a tangible connection to observable reality. Bohr's insight bridged the gap between theory and experiment, showing that the discrete nature of energy is a fundamental feature of the physical universe. Quantum jumps also influenced the development of later quantum theories. Heisenberg's matrix mechanics, for example, treated quantum transitions as fundamental events, focus on observable quantities such as energy changes rather than unobservable electron trajectories. Schrödinger's wave mechanics, while providing a continuous wave description of electrons, still incorporated the concept of quantized energy states, effectively embedding the idea of transitions between discrete levels. Bohr's introduction of quantum jumps created a conceptual framework that allowed these subsequent theories to thrive, providing a consistent explanation for atomic phenomena while guiding the development of mathematical formulations in quantum mechanics. It demonstrated that the discrete behavior of electrons was not a curiosity, but a central principle of the microscopic world. The phenomenon of quantum jumps also has practical applications that continue to impact modern technology. Lasers, for instance, operate by inducing electrons to occupy higher energy states and then stimulating their transitions back to lower states, producing coherent light. Fluorescent materials, LEDs, and other photonic devices rely on control electron transitions to generate light at specific frequencies. In each case, the predictability and discreteness of quantum jumps make the technology possible, illustrating how Bohr's abstract principles underpin tangible innovation. These applications highlight the enduring relevance of Bohr's ideas, showing that concepts formulated to explain atomic structure have far-reaching consequences for both science and society. Moreover, quantum jumps revealed a new understanding of probability and determinism. Unlike classical physics, where outcomes are predictable given initial conditions, quantum transitions are governed by probabilities. While the energy difference between levels is exact, the timing of a particular jump is probabilistic. This challenged traditional notions of cause and effect, forcing scientists to reconsider the limits of prediction at microscopic scales. Bohr's model, by incorporating this probabilistic framework, prepared the scientific community for the conceptual shifts required by full quantum mechanics. It emphasized that at the heart of atomic behavior lies inherent uncertainty, constrained by quantized energy levels yet subject to probabilistic rules. Finally, quantum jumps highlight the elegance and simplicity of Bohr's approach. By introducing the notion that electrons move discontinuously between defined energy levels, he solved multiple paradoxes at once: atomic stability, the origin of spectral lines, and the discrete interaction between matter and radiation. The concept is both intuitive and mathematically precise, demonstrating the power of combining physical insight with abstract reasoning. Quantum jumps provide a clear mechanism for understanding phenomena that classical physics could not explain, revealing the universe as a coherent, ordered system governed by discrete rules at its most fundamental level. In conclusion, the concept of quantum jumps is central to Bohr's legacy in quantum physics. It revealed the discrete nature of atomic energy, explained the origin of spectral lines, influenced the philosophical understanding of measurement and probability, and underpins a wide range of modern technologies. By proposing that electrons transition instantaneously between quantized energy levels, Bohr transformed our understanding of the microscopic world, bridging theory and observation in a manner that continues to guide scientific thought and innovation. Quantum jumps illustrate why Bohr's ideas endure as foundational principles in physics, highlighting his role as a visionary who reshaped humanity's understanding of reality. Bohr's contribution to quantum physics culminates in his revolutionary understanding of the duality between determinism and probability in atomic behavior, a concept that reshaped the very foundation of modern science. Classical physics had long been deterministic. If one knew the initial conditions of a system, its position, velocity, and forces its future could, in principle, be predicted with complete certainty. This worldview governed the understanding of planets, pendulums, and everyday objects, instilling a sense that the universe operated like a vast, predictable machine. However, the behavior of electrons in atoms defied this framework. While the allowed energy levels of electrons could be precisely calculated, the exact moment at which an electron would transition between levels could not. This tension between predictable structure and inherent uncertainty became a defining feature of Bohr's quantum vision. Bohr recognized that atoms were governed by rules that combined certainty and probability in a novel and unprecedented manner. The energy levels of electrons, the architecture of the atom, and the resulting spectral line were deterministic. They could be predicted, measured, and confirmed experimentally. Yet the act of transitioning between these levels, absorbing or emitting energy, was probabilistic. Electrons could reside in a given energy state indefinitely, but the timing of a jump was not determined by classical laws. This duality challenged the conventional notion that determinism was an absolute property of nature. Bohr's insight was that the microscopic world operates under a different logic, one where structured predictability coexists with stochastic processes. This principle became a cornerstone of the emerging quantum mechanics, influencing interpretation, experiments, and philosophical perspectives on the nature of reality. The probabilistic nature of atomic transitions also had profound experimental implications. Spectroscopy, the study of light emitted or absorbed by atoms, provided a window into these probabilistic processes. While the energy differences between levels were exact, the intensity and timing of individual photon emissions reflected the statistical distribution of many electrons undergoing transition. The observed spectral lines were sharp and reproducible, confirming the deterministic structure. Yet microscopic behavior underlying these lines revealed inherent randomness. Bohr's model reconciled these observations, showing that predictable patterns emerge from the collective behavior of probabilistic events. This understanding provided a bridge between individual quantum phenomena and macroscopic observables, illustrating how order can arise from apparent randomness. Bohr's ideas also influenced the philosophical interpretation of quantum mechanics. By demonstrating that probability is an intrinsic property of atomic processes, he challenged the classical assumption that nature is entirely deterministic. This led to the development of the Copenhagen interpretation, in which quantum systems are described by probability until measured, and the act of observation plays a crucial role in defining physical reality. Bohr emphasized that quantum theory does not describe reality in the classical sense but provides a framework for predicting the outcomes of measurements. This perspective fundamentally altered the way scientists think about nature, introducing a conceptual shift that extended beyond physics into philosophy, epistemology, and the broader understanding of causality. The duality between determinism and probability also provided practical tools for understanding chemical and physical phenomena. In chemistry, for instance, the predictable energy levels of electrons explained the structure of the periodic table, the formation of chemical bonds, and the reactivity of elements. At the same time, probabilistic electron behavior accounted for variations in reaction rates, excited state lifetimes, and the statistical distribution of molecules in different energy configurations. In physics, the combination of predictable structure and probabilistic transitions underlie phenomena such as radioactive decay, photon emission, and particle scattering. Bohr's insight thus connected abstract quantum principles to tangible experimental and technological outcomes, bridging theory and practice in a way that classical physics could not. This duality also shaped the development of quantum technologies. Lasers, semiconductors, and quantum computing devices rely on the precise energy levels of electrons while simultaneously exploiting probabilistic processes. In a laser, electrons occupy excited states in a controlled population, yet the emission of photons follows probabilistic rules that can be harnessed to produce coherent light. Quantum computers manipulate qubits, which exist in superpositions of states, with their behavior governed by probabilities yet constrained by deterministic rules of energy and entanglement. Bohr's vision of determinism intertwined with probability provides the conceptual foundation for these advanced technologies, demonstrating the enduring relevance of his insights to modern science and engineering. Bohr's exploration of this duality also highlights his methodological brilliance. He consistently balanced bold theoretical innovation with empirical grounding, demonstrating that even radical departures from classical thinking could be tested and confirmed through observation. By insisting that quantized energy levels explain atomic stability while accepting probabilistic transition, Bohr created a model that was simultaneously elegant, predictive, and experimentally verifiable. This approach exemplifies the essence of scientific inquiry, the ability to reconcile abstract reasoning with measurable reality, to propose concepts that challenge intuition yet withstand rigorous testing, and to provide frameworks that guide both understanding and application. The philosophical implications of Bohr's ideas extend beyond physics. By showing that reality at the atomic level is both structured and probabilistic, he challenged deep-seated notions of causality, predictability, and the limits of human knowledge. Nature is no longer a fully knowable machine. It is a system governed by rules that allow both certainty and uncertainty, determinism and chance. This shift has influenced not only science, but also broader intellectual thought, inspiring debates about the nature of knowledge, the limits of observation, and the interplay between order and randomness in the universe. Bohr's vision emphasizes humility in the face of complexity, recognizing that some aspects of nature are fundamentally probabilistic, even as others follow precise, predictable patterns. In practice, Bohr's duality principle has enabled scientists to make sense of phenomena that would otherwise appear contradictory. Atomic transitions, chemical reactions, radioactive decay, and photon emissions can all be understood as the interplay of deterministic structures and probabilistic events. By framing quantum behavior in this way, Bohr provided a coherent and comprehensive model of the microscopic world. He showed that the universe at small scales is not chaotic but follows precise rules, albeit with inherent uncertainty in the timing or path of certain processes. This insight has guided generations of physicists, chemists, and engineers, providing a framework for understanding and manipulating the quantum world. In conclusion, the duality between determinism and probability in Bohr's quantum thinking represents one of the most profound and enduring contributions to modern science. It reconciles the predictable structure of atoms with the stochastic nature of quantum transitions. Underpin the philosophy of quantum mechanics, guides experimental interpretation, and informs practical technologies. By revealing that the microscopic universe operates according to both precise rule and inherent probabilities, Bohr transformed the understanding of reality, bridging theory and observation, structure and chance, and ultimately cementing his legacy as a pioneering visionary whose ideas continue to shape the landscape of science today.